Okay, so let's do some examples of Lebec-dominated convergence theorem. So what's our assumption? Our assumption is, well, what are we looking at? We're looking at a sequence of functions, just like before. Okay, so measurable, whatever, that's not going to be the important part here. What we want to check is that we've got a pointwise convergence. Well, if we don't, it doesn't matter what the sequence is doing. You don't care for integrability then. All right, so pointwise convergence means that as n tends to infinity, and for fixed value of x, the sequence of values fn of x tends to f to some function f of x. Right, so as n tends to infinity. Now we don't have any hypothesis about the monotonicity of the sequence, but we have the existence of dominating function. Dominating function. Let's call that g of x, which is integrable. What does that mean? It means, so first of all, the integral part just means that the integral of g, well, in absolute value, should be in absolute value, is finite. That's it. And the dominating part, so it dominates the whole sequence. It means that whatever the n, so it must work for all indices n, I have that the absolute value of fn of x is bounded above by the value of g of x. Okay, so you find a function g of x that is above all the functions of my sequence. And in that case, it's very simple. The conclusion is the same as before. In that case, you have that the limit as n tends to infinity of the integral of fn of x dx is equal to the integral of the limit as n tends to infinity of fn of x dx, which is, of course, the integral of the pointwise limit f of x. Okay, and of course, this is going to be smaller than infinity because all the sequence is always bounded above by the g function. Okay, so of course its limit is also going to be bounded above by the g function. So let's make some examples of this. All right, so let me give you this sequence of function. Let's put fn of x is equal to x over 1 plus x to the n. First thing we need to do is to find the pointwise limit of this function. So let's do that. Well, you see you've got x to the n, so as n tends to infinity. What's happening? Well, the only term that depends on n is x to the n. And the limit of this depends on the value of x, of course. So first of all, we're going to restrict that to x in R plus. Okay. So if you want to be very rigorous, we should write our function times the indicator function of R plus. All right, so and what's then the limit of x to the n? Well, it's going to be depending whether x is greater or smaller than 1. Okay, so if, let's say, if x belongs to the interval 0, 1, 1 open, x to the n is going to converge to 0. Right? And if x is equal to 1, x to the n just stays 1. And if x is greater than 1, then x to the n tends to plus infinity. So what's the pointwise limit of my sequence? It's just simply going to be, so fn of x tends to, well, if x is between 0 and 1, to x over 1 plus 0, so to x if x is between 0 and 1. If x is equal to 1, it's going to be 1 over 1 plus 1, 1 over 2. If x is equal to 1. And if x is greater than 1, we get x to the n goes to plus infinity, so the function just simply goes to 0 if x is greater than 1. So well, we can even plot that. So that's 1. And our function is going to be, well, x between 0 and 1, then value 1 over 2, and then 0. Okay? Which has, in terms of integration, that's a nice one, right? But do we have that the limit of the integral of x over 1 plus x to the n, which is less trivial to compute, is equal to the value of of the area below that red curve, which would be, I guess, 1 over 2. Right, so that theorem is going to help you state that limit as n tends to infinity of the integral of on r plus, so we're restricted to r plus of x over 1 plus x to the n dx is indeed equal to the integral of this function, and which is 1 over 2. Okay, so we still don't know it yet, but that will be the conclusion of this theorem. So let's see. We've got our sequence. It's neither increasing nor decreasing because probably it's going to be increasing between 0 and 1 and decreasing after infinity. After 1, I mean the sequence fn of x for fixed value of x. If x is between 0 and 1, the corresponding sequence of values fn of x is going to be probably increasing, and after 1, decreasing. So we can't apply Beppe-Levy monotonous convergence theorem because it doesn't have monotonicity on the whole of the domain, but we will probably be able to apply Lebec dominated convergence theorem. So what do we need? We just need a dominating function. So let's find a dominating function. So g of x. The main requirement, so g has to be greater than all the fn of x for any x. And moreover, we need that the integral of g, absolute value, if I need that, is greater than 0. Oh, sorry about that, is finite. Okay, so let's see what we have. Our function has several parts. We have the between 0 and 1. I can bound it above by the x function, simply because, as we said, x divided by 1 plus something not 0 is going to be smaller than x. All right. So I probably can take g of x is equal to still x between 0 and 1, because this corresponding sequence is increasing between 0 and 1. Whereas on the other side, it's just decreasing. So I need to find something that is above x over 1 plus x to the n for all n, and for all x is greater than 1, for all n or for some n at some point. So first thing, this is going to be, of course, smaller than x over x to the n, which is 1 over x n minus 1. Okay, great. And next thing, we need this to be integrable. So if you remember what we worked on last year, we have that 1 over x to some power is integrable on 1 plus infinity, if and only if p is greater or equal, strictly greater than to 1. These are the Riemann integrals. Okay, so if we put n greater or equal to, well, let's make 3, so that n minus 1 is 2, that's okay. So let's say that we put g of x is 1 over x x2, that's fine. And for x greater than 1, and then we will have that g of x is greater or equal to fn of x as long as n is greater or equal to 3. And that's right, because we don't really care what the f1 or f2 functions are doing in that case. We just want to know what's happening at infinity. So if n is greater or equal to 3, we really have that g of x is greater than, well, even the absolute value, if we want to go with the theorem. All right, so we've got a dominating function. We have that g of x is integrable and dominates sequence fn of x. And so, conclusion of the theorem, we have that the limit of the integral of the fn of x is equal to the integral of f of x, okay, and which we said was equal to 1 over 2.